In this paper, we present an analysis of multimodal interaction strategies for LLM-assisted manipulation of 3D scenes. This work is a joint effort from researchers in the University of Cambridge and Coburg University of Applied Sciences. In this paper, we investigate user strategies, barriers, and propose design recommendations for improving LLM-assisted 3D scene editing systems. We begin with a brief introduction of the background and motivation of our work. Consider the following example where you have a scene with multiple objects. Some objects share the same properties, and objects can be bulk edited to match a target appearance. We hypothesize that in such cases, LLM-assisted speech and pointing systems have the potential of outperforming traditional interaction techniques. This potential of LLMs for 3D content has been studied by many previous works such as LLMR and GazePoint-AR, which demonstrate many application prospects of such systems. However, there is still a research gap in understanding interaction patterns, user behavior, and interaction barriers of such LLM-assisted systems. Therefore, we clarify that our work is not the typical LLM for X paper, but instead focuses on bridging this research gap in interaction studies by proposing a technical system. To support our study, we designed AssistVR, an advanced speech support and interactive system for virtual reality. AssistVR is implemented with two models, the Microsoft Azure Conversational Language Understanding Service, or Azure CLU, as well as OpenAI GPT-4 Omni, or GPT-4o. In the training phase, only Azure CLU is involved. Utterance data are labeled with intent and key entities and sent to the model for training. In the deployment phase, both models are involved. Speech input is recognized, and Azure CLU classifies the user intent and extracts key entities from the user input. If the intent falls under a predefined category, the recognized intent and entity is sent to Unity for post-processing. Otherwise, GPT-4o catches the exception and provides a natural language response based on the user input. Now we will move on to the setup of our study. The study is conducted with 12 participants, 6 male, 6 female, aged 22 to 35. Participants used an Oculus Quest 2 headset in a Unity-based VR indoor scene. The main goal of the task was to edit the scene to match two types of target appearances, namely task types A and B. Task type A involved making all blue objects gray, making all cotton objects leather, and changing the carpet into white pattern. The first two instructions were given verbally, while the third instruction was given in the form of an image. Participants did not know that they could refer to the carpet as white pattern. The purpose of including the carpet is to simulate cases when objects are difficult to reference verbally. Task type B is a variation of task type A. It involves two verbal instructions to change the color and material to a different state, and a non-verbal instruction to change the carpet to match the target appearance. The study involved a practice trial, where participants familiarized with AssistVR. Task 1, where participants edited the scene and were instructed to explore all available colors and materials to find the most efficient strategy, and Task 2, where participants edited the scene based on the most efficient strategy they found in Task 1. Participants interacted with the system to find out which commands were supported, and the sequence of task types A and B were counterbalanced across all participants. The entire study lasted for around 1 hour. In terms of performance results, the study revealed performance improvement and reduced load in Task 2. Performance improvement is reflected through the improvement of task completion quality by matching the target scene better and the reduction in task completion time. While participant performance is expected to improve over time, the scale of this improvement indicates that users adapt quickly to the system. Reduced load is reflected through a significant drop in NASA TLX task load rating in Task 2. However, no significant differences were found in usability and user experience between both tasks. The study revealed two main interaction strategies: incremental exploration, consisting of step-by-step individual object edits, and bulk modification, consisting of group edits based on shared properties. This is an example of the incremental exploration strategy adopted in task type A.
Make the bed gray.
Changing bed into gray.
Make the sofa gray and made of leather.
Changing sofa into gray leather.
This is an example of the bulk modification strategy adopted in task type B.
Select all blue objects.
Selected small vase, vase, bin, book, pen, pen holder, wall, table, wall, carpet.
Make them purple.
Changing small vase, bin, book, pen, pen holder, wall, table.
If we visualize the interaction strategies on a timeline, using blue for bulk modification and orange for incremental exploration, we can see that many participants transferred to the bulk modification strategy in task 2, as shown in the right figure, compared to task 1 as shown in the left. We extract a list of 7 behavioral insights. For example, users tend to prioritize visually distinguishable features, and objects with unclear goal states tend to be edited last. Please refer to our paper for more details. We also summarize interaction barriers. These include barriers in speech recognition, barriers in the clarity of feedback provided, as well as barriers when users phrase their commands. Our study also provides implications for future designs. We confirm prior findings in multimodal interaction in the context of LLMs, and highlight the importance of mechanisms to build user trust and handle errors. These implications guide future work towards new directions, such as high-level 3D content manipulation tasks, techniques to resolve ambiguity, and measures to incorporate more advanced multimodal techniques. In summary, our work demonstrates that LLM-assisted systems have the potential to allow users to improve performance significantly with very limited external guidance. We summarize patterns when users interact with LLM-assisted systems in a scene editing task and highlight interaction barriers to propose design implications and avenues for future work.